Hello, Ram. Welcome to another live coding stream. Today we'll be looking at magnetic tiles, like we did a few weeks back. But this time we'll be looking to segment them instead of classify them. So hopefully that will be pretty cool. While segmenting them, I'll also show off the new unit feature, or component rather, and a bunch of things related to that, which makes the segmentation even possible. So yeah, let's jump straight into it. I'm gonna show the dataset real quick. It's very similar to what we went through before, if you guys saw that stream or video. But the entire dataset is essentially looking at these magnetic tiles through an assembly band, for example, and trying to find defects. And what we did before is we have these different folders, or these different classes. And we were essentially just looking what kind of anomaly it was. Was it blowholes, breaks, cracks, frays, uneven, or just nothing? No anomaly at all. So we're looking through those. But for this time, instead of doing that, we'll just look at these first few folders, and then we'll look how they segment. So we'll teach the model these masks, and hopefully by the end of it, the model will be able to tell not just that it is an anomaly, but also where in the image there is the anomaly. The CSV file will look something like this. I have a few different here now, but there's one here which does not use the free. We don't really need to teach it on no segmentation or no anomaly, since we're specifically trying to teach it locations. And if we open this one, it'll look something like this when we have segmentation data. My computer's just freezing a little bit. But while that one is freezing, we can see over to the left we have images, which are the PNGs, and then we have the masks over to the right. So that's how we structure up the CSV file here. We send images in, we get images out. There we go. All right. So with all of that, let's jump into PerceptiLabs and start building out the model. So I'll just load it up as usual. And I did make a slight mistake creating the CSV file. The PNGs turns out to be the masks and the JPEGs the images. But to fix that, I'll just put these as targets and this as inputs instead, and problem solved. And then there are a few things we want to make sure we have for doing segmentation. So first of all, you want to make sure to normalize it, especially in masks, if it's since we're doing binary segmentation, we want all the background pixels to be zeros and all the foreground pixels or the object pixels to be ones. Another way of doing binary segmentation is having two different channels with a similar setup, but I found it much better to have a single channel and then just have zeros and one in it. Got a question: images and masks are the same file? Yeah, the masks are PNGs and the images are JPEGs. So yeah, the same name, a little bit confusing, but it's different images. And I'll see it when we load the model in here as well. And the second thing is we're going to use a unit. unit has a very interesting structure. To try to illustrate it, I should have prepared an image for this, but you build the unit. It looks exactly like a U, that's from the name. So first you have a bunch of convolutional layers, which makes the image smaller and the feature maps larger. And then you reverse that. You upsample it or transpose it to get it back to its normal input size. And then you connect each of these layers, as you can see them. You connect from the input layer into the upscaling layer, and that's the unit structure. What this does, though, is if the downscaling and the upscaling has a rounding error, meaning that your input is not divisible by 2 to the power of 5 if you have 5 layers, you'll start getting crashes. So easy solution, just make sure that your size is 2 to the power of something larger than the layers. So 56, for example. And I'll do the same here as well. I'm normalizing these as well. The unit has a tendency to learn better if the images are normalized. Especially the initialization of the unit. It's very easy that the initial output is very large. So anything you can do to kind of narrow that down, the better. And it seems that to be pretty standard, just to do some normalization. And of course, I'll make sure that these are 256 by 256 as well. All right, so here we have the inputs and the targets. We can see here how they look like if you didn't quite catch it in the folders, but we have an input image. It has some kind of anomaly or a defect, and that's the one we're highlighting. Could we add the normalization pre-processing as a layer in the model itself? You can, for sure. We don't have it as a component quite yet, but it's very easy to drag in a custom layer and just divide by the max in the image. We used to do that before we had the pre-processing inside the data wizard. So if you prefer to do that inside of this workspace, that works. The pre-processing will go into the model though. So if you do normalize it, that will follow along when you export the model. So you're not losing out by having it inside the data wizard. So earlier in the summer, we used to build units, and we built them manually, which meant how many? 10, 12 convolution layers stacking this structure. But since then, we now added this unit component. So all we really need to do to use unit is plug this down, and we have something which runs unit. It's very similar to the pre-trained components. We have the ResNet and Inception and so on. Then I just connect this up. And to quickly go through the different settings before we start running it and seeing how it works, we have something called attention, and that is if you want to run a unit with attention layers. I think we will do that at least once because it performs pretty well. Number of labels is how many outputs you want it to have. So if you're doing a multi-class segmentation, you want to increase this so it matches. For now, just one is fine. Stack number down is how many convolution layers when going down you have per row or per layer is a bad word. There are so many layers in neural networks, but per level, I suppose. And stack up is the same, but when you're going up instead. Activation is activation. Output activation is the activation for the very last convolution. It's default set to softmax. Softmax is great for multi-class segmentation. It's awful for binary. Don't use it for binary. It will act as a cap, so anything outside 0 and 1 just becomes 0 and 1. And that will make your gradients go to 0. So let's change that to sigmoid instead. Batch normalization works exactly like batch normalization does. Pooling, unpooling is just different pooling layers when you're going down and up in the unit. And backbone is if you want to use a pre-trained layer as the encoder, as the down part in your unit. So we got VGG, RestNet, EfficientNet, essentially the standard Keras layers. And that's everything. So, oh, there's one more setting that's not in here. Filter number. This decides how large your unit is and the number of filters per level. So this says that first level will have 64 filters, second 128, third 256, fourth the bottom level 512. You can easily add number of levels by doing like this. We haven't added it as a setting yet, but if you're looking for how to make your unit larger, just go in there. Alright, so let's finally start running it. So this data set we have is surprisingly difficult. And we'll see we'll probably see it not working very well with just a vanilla unit. But we'll try something a little bit different after that. We do also have two different losses, dice and Keras dice. They're calculated slightly different. Keras dice will give you a slightly smaller loss compared to dice. We're going to merge them into one very soon. But for now, you can try both and see if you have any better experience with one or the other. If one works, generally the other seems to work. So let's run it. Probably just take a second to start up. And there we go. Actually, the target is the first one. Alright, so this is the visualization for the unit. You have prediction overlaid by ground truth, so you see a slightly brighter part, which is the defect. This is the ground truth for the label. Then we have the prediction, which is awful. As you can see, the gradients are flat. So again, this is a very difficult model to train. So we're going to actually, let me just stop it. So we're going to try something else. Then we have IOU. So IOU is intersection over union. I believe that's correct. Essentially, it's how much your prediction, your predicted segmentation overlaps with the labeled segmentation. So you're not measuring just how many pixels are correct, you're measuring how well they're overlapping, which gives a much better measure of accuracy. and then we have loss. So yeah, this one did not work that great. So let's try something slightly different. We can try quick with a backbone if we throw in a VGG. And right, here we'll see a crash. This crash tells you that we're trying to feed in grayscale images when it's expecting RGB images. And it's expecting RGB images because it's frozen. And if it's frozen, it has some weights which you can't really change. This is solved though. We can either use the in a previous live coding, I used a little script in a custom component to turn it into RGB. One of our dev advocate though had a much nicer solution, which is just to take a merge component and drag this in like this and concatenate, and voila, you have RGB. So credits to David for that one. You'll see him around the forum. And then we connect it up, and let's throw in batch normalization as well. That usually helps performance on these ones. Then we run it, and we can leave everything as is, and we'll just see. Well, the first thing we want to see is if the gradients flatten straight away or if they actually do work. Alright, so far it's looking promising. Now we do need to fix this one a little bit. It's very hard to see what's the ground truth. We should probably color it red or something. But another thing we can do now that we see, and there it died. Alright, never mind. I was going to show that you can just look at the target here instead. Oh, okay, so for some samples it's just not doing well at all, it seems, and for some better. So you can let it run a little bit and see what happens. But if you click on this target component, you'll see what this image should be. So you can just compare the predicted with the output to get a sense of how well it's moving. Obviously it won't be a perfect representation. You want to look in IOU to get much better overall estimate on how it's going, but just as a sense on what's actually happening. And yeah, Harry, we're very happy to finally have the single unit component. It's a lot easier to use than to build it from scratch. I think this one is using GPU, yeah. It's still taking a bit of time though. As soon as this one is done as well, we have we added tests for the unit also, or segmentation more specifically. So we'll take a quick look at those after training finishes. Well, it seems to be learning at least. The training IOU is going up, but the validation not so much. So it might not be. Well, it's clearly not generalizing as well as it should. Some it fits perfectly though. And take a quick look at the gradients again. Which looks decent. I did have one scenario where I was testing it out where the gradients were just exploding. Which is actually the first time I've had that happen in PerceptiLabs. I don't remember the exact architecture though, but they were going quickly towards the millions. And then it crashed. We're also going to turn this one probably into a heat map. It's you can see the whites are where it's predicting close to 1, and then you have some grayish areas which are predicting somewhere in between 0 and 1. But turning it into a heat map will make it a lot easier to see, both because of the color difference, but also you could actually hover over it and see each pixel, what it predicted. But that's in an upcoming update. So a question, what do we mean with single node? So the entire unit is just in a single component. As before that, you would have to actually, let me see if I can show a quick image of how the unit looked like to build before that. 1 second. Realized it finished training, but let's see real quick. We capture yeah, that did not work. Never mind, I'll try towards the end to show you, but it's it was quite large, while now it's just a single component. Anyway, the training finished. So now I can run the test on the model. Select the model, and we both have metrics for it, just like classification. And we also have an output visualization. So if we run both of those, we get something like this. So here we can see the intersection of a union. Not very good on the testing data. As we saw in the validation, it was barely improving. Dice coefficient and Kira's dice coefficient measured slightly different, but the general, if one is good, generally the other one will be good as well. One is a bit more focused on the true positives, while the other one on the false positives, I believe. Don't quote me on that though. Then we have this thing. So here we can see the input, we can see the target, we can see the prediction, and we can see how the prediction overlays the target or the input. And they're ordered, so you can see the loss here, and the loss is essentially how much error they have. And they're ordered so you can see the best one, or the 5 best ones, and then you get to see the 5 worst ones. So you can look through and see where it performed well, and if these are the best cases, the bad ones are probably not going to be so good. And then you can see the worst ones where the loss is almost 1, which means almost completely faulty. And we can see here that it's really having difficult with these single dots. So one thing which might help that is a attention model, so it can focus on better. We got a question, where to add code to disable a layer training and add custom weights. So for any component, you can just press open code and you'll see the code of the component. Call is whatever is executed when the component is ran. Build is just a support function. Here it builds the model, and it makes everything, all the variables inside here are accessible in call. So it's just a way to initialize the component. And ignore these two. So if you have some already existing weights, you can always just load it in using TensorFlow inside this component, and it will work like it would in standard TensorFlow. We are also introducing at some point a component which will do it automatically for you. We can just point at a .pb file. Anyhow, let's get back to this one. And I think all of this is fine. And then we just increase it slightly. There we go. And this one might have some more interesting results. And while this one is training, I'm gonna try to show you the unit. See if I can figure that out. Let me put this one on something interesting as well. You see the gradients here. So the gradients on this one I don't think will die very quickly. So we can look at the target and the prediction instead. It's really early, but at least it's not predicting completely white, which is too often the case. Okay, how about this? There we go. All right. So this is how the old unit used to look like. And just to give some perspective, this entire part now is just a single component. We are going to make it a little bit different, or give the option to break out this single component though. And what that would allow is to have this one as an encoder, or you can have this one by itself, and then you can add multiple of these convolutional layers. And that means that you can have multiple targets, which means that you can do multi-classification by having multiple binary segmentations. Sorry, multi-class segmentation by having multiple binary segmentations. Or you can have the target be some other type of data and see if that works. But yeah, let's go back to the training. Alright. So let's see. It's doing... it's not looking amazing so far. But it's still early in the training. And I think I clicked on the unit because I wanted to check the gradients real quick. Unfortunately, I can't do too much else while this one is training. But we will soon get our cloud platform up. And that will be distributed between machines, so then you just spin up training after training after training. Not have to worry about that. Okay, it does seem like this one might have performed worse than the first one I showed, which was unexpected. The performance I got from this one a little bit earlier in the week was quite a bit better, but we're still getting something out of it. And I suppose this means that at the very least it works well without the attention model. It's probably the VGG which helps a lot. And the other thing we edited for this one was the depth of it. So if you remember the picture I just showed, you could clearly see the levels there. So in the image I showed, there was 5 levels, which we're using here now as well. But in the earlier test, we used 4. Alright. So we can run a test on this one as well. I'm not expecting anything amazing out of it, but it will be fun to see the best predictions it does. Yeah, it's I would say the last one probably was a bit better. This might be one of those you need to train a bit longer, maybe around 50 to 100 epochs instead of just 10. Since the gradients were still changing fine by the look of it. So you could probably train this for a bit longer and hope that the validation goes up. Alright, but that was everything I wanted to show for today. Thank you everyone very much for watching, and I hope you guys enjoy the unit and the segmentation. Let us know if you have any feedback. Hit us up in the forum or in the Slack. But other than that, have a great day. Take care.